In this video, we're going to be looking at some important ideas like the concept of growth, exponential growth, and exponential functions. This is the first lesson of Unit 3, Exponential Functions, as part of my Grade 11 Functions course. If you want me to teach you this entire course, visit my website, tutor.ca, and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section of Grade 11 Functions. I hope you enjoy the video. Hello everyone, I hope you're doing well. Welcome to Lesson 15 in the second teacher program. It's course on Grade 11 Functions. Here we are taking a look at the nature of exponential growth, which is section, similar content to section 3.1 from the textbook that we are following, or whatever textbook you're following. We're talking about the nature of exponential growth. So today we start our new, I always say today, but of course you could be watching multiple lessons a day. That doesn't make much sense. But in this lesson, we are starting our new unit, Unit 3, which is about exponential functions. Okay, we're going to talk all about these specific kinds of functions called exponential functions. Okay, and those are functions with a certain quality to them, and they have special properties, and they have a special kind of equation that describes them, and so we will talk about that. So let's talk about the types of functions you know so far, right? So you definitely know linear functions. Okay, linear functions are things like f of x equals 2x plus 5. You've studied this in grade 9. You started studying this in grade 9, right? So you studied it under the idea of y equals 2x plus 5. But honestly, I think to me at least, it makes more sense to think of it as a function, as in we're putting some x value in, and we're getting some f of x value out, right? And then we graph that instead, right? So anyways, there's just an example, right? Qualities is that the equation contains a linear expression, which what that means is that the highest power of x is 1, right? So x to the power of 1 there. And so any kind of combination, as long as x to the power of 1 is a linear function. Okay, you also know about quadratic functions. We talked a lot about that in Unit 1 of this course, right? So quadratic functions. So you talked a lot about quadratics last year in grade 10, but here we're talking about quadratic functions, which are quite similar. So that's something like 2x, or whatever, x squared plus 3x minus 1, right? Main quality is that the equation contains a quadratic expression. Okay, what that means is that the highest power of x is 2. And another thing to note here is that the graph is a line, right? You know that the graph of a linear function is a line, and that the graph of a quadratic function is a parabola, right? So we've studied these two in a lot of detail. Now, I've also mentioned to you the root function, right? That's an example I use a lot because I think it's a good example. So that's any function that has a square root in it. So that's like maybe something h of x equals, I don't know, 2 square root x minus 5 plus 1. There you go. So the equation contains a radical. And there we go. The graph is kind of like a sideways half of a sideways parabola. Okay. And there's many other kinds of functions, right? We have a whole bunch of them. You can come up with any kind of function you want. Okay, one more thing, we also have our rational functions, okay, which are functions like, I don't know, q of x equals 1 over x plus 1, right? So you have the independent variable in the denominator of a fraction, right? And this makes asymptotes. Okay, so we're gonna we're gonna study a lot more about what asymptotes are this unit, but asymptotes are essentially where you have a graph that's approaching either the x or the y-axis, but never actually touches it. So you see this goes up forever, approaching the y-axis, this goes up forever, approaching the x-axis, but it never actually touches it. So that's your asymptotes. What I'm just doing is just laying out essentially the groundwork here, right? What do we know? We've studied these kinds of functions, right? This we mentioned at the beginning of Unit 2. This I've been mentioning the whole course, and this is grade 9 essentially, so I've mentioned that whole course as well. And this is Unit 1. We talked about quadratic functions in Unit 1. So now we are going to move on to a brand new kind of function, okay? And we're going to use everything we learned in Unit 1 and Unit 2 to talk about this new kind of function, okay? Okay, and that new kind of function is called an exponential function. Okay, so an exponential function. Okay, and maybe what jumps out at you is the word exponent in there, right? There's an exponent. We have exponential. The word exponent is kind of lodged into that word, so maybe it's a function to do with exponents. That's a very good guess, and that is approximately what it is. And so we are going to spend the rest of this unit talking about how do we use exponential growth, how do we use exponential functions, and the specific behavior that they have compared to these other kinds of functions. Okay, so the graph of an exponential function is nothing like the rest of these. Okay, and so I think we're ready to actually jump into a little bit of, start talking about what this stuff is. Just a little introduction. But I just want to mention that exponential functions are used a whole bunch. Like all these functions are used in math in math obviously, but in if you're interested in engineering or in other kind of sciences, knowing how to work with functions is essentially the basis of a lot of research, right? You look at data, you compare data, and all these kinds of different behaviors might pop out from the data. Linear, quadratic, root. Root is not really the technical name for that, but rational. And then exponential is another really big one. Now, a lot of things in nature happen in an exponential way. And so that's why we spent a whole unit talking about it, because it's the most kind of related to nature. Okay, enough of that. Let's actually get started on exponential functions, the introduction to exponential functions. First, what we have to introduce is exponential growth. Okay, what does it mean for exponential growth? Now, what does growth even mean, right? We haven't defined what growth is, right? Maybe you imagine like something getting bigger, right? That's kind of what growth is. That's what we know of it. Maybe something living getting bigger. And so that's the idea. First, I want to just talk about linear growth. Okay, so linear growth, just to give you an idea of what I mean by growth. For example, if I have a graph that looks like this. Now, I'm going to maybe do this in Desmos, just so that I can just have a easier time with what's going on here. So if I have a linear equation like this, maybe, okay, or maybe I won't make it that big, like this. We'll zoom out a little bit. Make that a little bit bigger. Okay, so I'm going to see all the x-axis marks. Maybe I can't. Okay, there we go. That's good. So if I take a look at just that section like that, okay, and I try to think about how is the function, right? So this function right here is f of x equals, it was 5x. F of x equals 5x. So first of all, that's a linear equation, right? The highest power of x is 1. And now, to think about what I mean by growth is if you start at some number, okay? Start at some x value, I should say. It has some corresponding f of x value. For here, f of 0 equals 0. That's why we have a point there. But if you take one step along the x-axis, to the next x value, add 1 to it. From 0, you go to 1. How much did the height of the function change as a result of that one step? In this case, it was 5, right? And so we can say that the function grew by 5, right? So the function grows by 5 units when going from x equals 0 to x equals 1. Right? Because when I go from x equals 0 to 1, I grow by 5 units. The function, the height of the function increases by 5, going from 0 to 5. And let's see if that happens again. If I go from x equals 1 to x equals 2, right? Well, now it has a height of 10 here, right? Which is another 5 units up, right? And then here, if I go another step, right? If I go another step here, it's at 15 units, right? That's a height of 15 here now. So it's going another 5 units up. So every time, right? So linear growth is essentially that the function goes up by some set amount every time we increment the input values. Okay, so increment means bring up by 1. Right? So increment 5, you get 6. Increment just means go up by a little bit, by 1 whole unit. Okay, so the function goes up by some set amount every time we increment the function. Increment the input values, I should say. Now, this isn't always true. You know, quadratics do not grow like this. They grow in a different kind of way, but it's not the same number every time. Okay, and so I'm kind of hinting at ideas here. So if I just give you a little foreshadowing, I'm kind of hinting at some calculus topics here. This is kind of what calculus studies, is how much do functions grow, right? And how do functions grow? That's maybe one half of the beginning of calculus, is how do functions grow. And so, but right now, all I want to do is focus on linear growth and exponential growth. I want to compare how those are different. All right. Okay, so just to give you, just to like set the basis of what does growth mean, it's sort of like the way a function changes every time you increment the x value. So I'm going to write that down here. So growth is how does the function change every time you increment the input value. Okay. Does it go up? Does it go down? By how much? By the same amount every time? By a different amount every time? But maybe how do you calculate that different amount? These are all ideas that we talked about in calculus, at the beginning of calculus. And so right now, that's sort of the idea that I want you to kind of grasp at here. Right? Okay, so let's start with an example. And this is going to actually dig us into what exponential growth is. So the idea that I want to compare here is if you were getting paid for a job, okay? There's two payment plans. Okay, we're going to look at this example here to kind of lead us into talking about what exponential growth is. So let's pretend like we're getting hired by some employer, and they give us two payment plans for how we can get paid for our work at this place. First one is just a nice, normal $15 per hour. Okay, that's pretty standard. Every hour you work, you get another $15. Or you can go for this kind of trickier one. You get $1 for just walking in, without even working. You get $1 for just walking in. And for every hour of work, they double how much you get paid. Okay? So essentially, we're trying to determine which one is the best for someone who wants to work 12 hours. That is our goal here. Okay? So to begin, let's make ourselves a table of values for each of these payment plans. Okay? So we can see for the first one, I'll call it number 1, right? I can make a table of values, one column being the number of hours worked, and the other one being the pay. So let's start at 0 hours. So if you work 0 hours and you get paid $15 an hour, you get paid $0. 1 hour, you get $15. 2 hours, you get $30. 3 hours, you get $45. 4 hours, you get $60, and so on, right? So on. We keep going here. So hopefully you're able to complete the table here. I'm just going to replace it with a nice typed up one that I have here. So if I just replace this, this is the idea. And it's the linear pay, essentially. This is what's called the linear pay. And it's linear because, like I just discussed up there, for every increment in the independent variable being the number of hours you work. So every time that goes up by 1, the dependent variable, the total pay, goes up by some constant amount. Right? So notice here, we're going up by $15 every time you work an extra hour. And that's exactly what it means to work for $15 an hour. Right? Okay. So, and $15 an hour is a standard pay, a little bit more than standard pay for a minimum wage job. So we can see up to 12 hours here, you get $180. Okay, so if you work for 12 hours, you get $180. That is essentially the idea here for linear pay. Now, what I want to compare is the second option, the kind of more interesting option, I'd say, right? So the more interesting option has the same table of values, right? We're going to compare the number of hours worked to the pay, and it's going to give some interesting results. So if you work 0 hours, you already get paid $1, right? If you just walk in, they pay you $1, right? Okay, but then if you work an hour, they're going to double it. So it's going to be $2, right? You're going to make $2. If you work 2 hours, they're going to double that. So you're going to work 4 hours. I mean, you're going to make $4. If you work 3 hours, they're going to double that. So you make $8. If you work 4 hours, they're going to double that. You're going to make $16. Okay, making progress. I don't know if we're going to overcome linear pay. I mean, right now, for working 4 hours, you only make $16. That's not very good. For linear pay, you work 4 hours, you get $60. Okay, well, let's continue. 5 hours, they're going to double that, so you make $32. Okay, better. 6 hours, you make $64. Just double that. Okay, well, we're getting closer. 6 hours, $90, still better. 7 hours, $128. Ah. For 7 hours of work here, you made $105. So now we're making more with this second option, right, which is exponential pay. So let me pull up a table for this one as well. Okay, and here is our exponential pay. So we have our nice table here. Again, just comparing the left side, which is our number of hours worked, which is our independent variable, to our dependent variable, which is our total pay. So let's answer our question. If you work 12 hours, what should you pick? Linear pay, you make $180. Exponential pay, you make $4,096. I think it's a clear winner here, right? Clear winner about what's going on. But I think it's still interesting to compare how this happened, right? Because if you look at it, up until the 7-hour mark, which is right here, up until the 7-hour mark, the linear pay was winning, right? 90 is bigger than 64, 75 is bigger than 32. The linear pay was making more money than the exponential pay. But then all of a sudden, the exponential pay makes wildly more than the linear pay. For 8 hours of work, well, let's jump to 9. For 9 hours of work, right, the linear pay makes $135. Exponential pay, $512. So there's something interesting going on here. This is linear growth, which is what we've studied a long time. This is linear growth. And this is an example of exponential growth. That's an example of exponential growth. To understand this more, I'm going to look at two things. One is going to be the graph, but before we do that, I want to look at another thing. It's just how much is this total pay increasing by every time we increment the number of hours. So we increase here by 1, right? Oh, I'm just realizing maybe you can't see the corner of the screen. No, you can just not see the word pay, which is fine. We go up by $1 here. You go up by $2 here, right? Go up by $4 here. Go up by $8. Go up by $16. Go up by $32, right? So the amount that we go up by for each increment of the number of hours worked, right, is going to be different for the exponential pay. But for the linear pay, it's the same. And I'm realizing now that maybe there should be a 0, 0 term at the start there. I just forgot to put that in the table. So, but if you work 0 hours, you make $0. That's pretty standard. So hopefully you can get away without seeing that there. But yeah, that is essentially the idea here for what we have as exponential pay. Let's take a second and graph these two relations here. All right, so I'm going to go to Desmos. I'm going to use Desmos to help us out. And I'm going to switch that to 7 and then hide this. So let's start with our linear pay. Our linear pay will look like this, right? So if you look, every time we increment the number of hours worked, that's the x-axis, our y-axis, the pay, goes up by 15. Okay, so an hour worked, $15. 2 hours worked, 30. 3 hours work, 15 more. 4 hours, 15 more. 5 hours, 15 more than the last, right? Now let's take a look at our exponential pay. That will look like this. Okay, so I'm going to hide that now. That will look like this. Now, notice, up until the 7-hour mark, right? Up until the 7-hour mark, linear pay is higher, has more pay, right? Literally the graph, the dots are on top of the exponential pay, right? So you can see it's higher pay here. But after that, well, the exponential pay just goes way up there, right? See that highest point? See how much higher it is than the linear pay? So there's this kind of nice curve happening here, and that's kind of what exponential growth is always going to look like. It's going to be this nice kind of curve that goes, starts out maybe a little flat, and then zoop, goes up really fast. So that's essentially what I wanted to point out to you here, right, is this kind of form like that. Right? So first quality to notice is that we start out growing pretty slowly, and then we end up growing very fast. See, the growth here is huge compared to linear pay, way more than 15. Right? We go from about 250 to 500, so about 250 growth there in pay. And that comes from the fact that we're multiplying, right? We're doubling. Okay, so that is the visualization that I wanted to give you. Now, let me just see if there's anything else I should mention. Yeah, so the next step is I want to determine the equations for both of these. Now, linear pay is something you've done for a long time. So let's take a look at linear pay. Well, linear pay is going to be in the form y equals mx plus b, right? Or, you know, we can say f of x equals y, f of x equals mx plus b. Right? F of x is our y values now, right? So we can just replace it like that. Same thing either way. M is our slope. M is the amount we go up by each time. So that's going to be 15, right? We get paid $15 an hour. And B is our y-intercept. How much do we get paid for $0 of 0 hours of work? We get paid $0, right? So B is 0. So 15x. So that is our linear pay. F of x equals 15x. In fact, I'm going to make a little bit of a notation change here. Now, this function is the same as p of n is equal to 15n. First of all, I just want you to notice that that's the same thing. I just changed the letters. But on purpose. So the p represents pay. And n is usually the letter used there instead of x when you specifically want to mean integers. Okay? So only integers can come in. I never said that you can work an hour and a half and get paid an hour and a half worth of work, right? I only said that you can get paid for working an hour, 2 hours, 3 hours. That's all we know. So we only know about the integers if you work a whole number of hours, right? And that's going to be the same thing here for exponential pay, right? Well, we're only going to know what's happening if you work a whole number of hours, right? We don't know what it means to work an hour and a half yet, right? Well, we know what it means, but we don't know what kind of pay you're going to get in terms of this payment plan, right? They didn't talk about that. So here we have this equation. P of n is equal to 15n. That works for this one. And I can, we can write it here. That's going to describe this right there, right? I could turn that into P of x equals 15x. And again, all I did is change a symbol, right? I'm not really changing anything. But what I'm saying now is that the input can take on any value. And that would look something like this, right? But again, I mean, I never said you could work a negative number of hours. I never said you could work an hour and a half. I only said you could work 1 hour, 2 hour, 3 hour, 4 hour. So we're going to stick to the integers here, right? We're going to just stick to these integers like that. Now, I can change the graph a little bit, right? I can redo the graph, and I will do that by, first of all, just putting the x equals 12 line right there so we remember where it ends. And I think if I just make this ... if I just make it a huge number like 3,000, right? This will go on for a very long time now. It won't go on forever, but it'll go on for a very long time now. And I can do the same thing here for this one. There we go, right? So this will keep growing exponentially. We can see points keep going up, right? But there's that much. Okay, so essentially now, right? That's where we stop counting though for our question, right? But I can continue this function. This is a function that takes in integers and gives you a pay. P of n is the purple dots. So P of n are the purple dots. Purple dots. This is the line connecting all the dots. If we were able to work negative hours and half an hour and in half-hour chunks or in any other chunks we want, right? But I never said that. Okay, the reason I'm making such a big deal about this is because it is a big deal for exponential pay. Okay, because I really, if I just asked you right now, how much would you make if you worked an hour and a half? You might be able to figure that out for linear pay, but what would it be for exponential pay? I mean, I don't know. I don't know yet, and I don't expect you to know yet at all. So that's what we're going to talk about in the next coming sections. But for right now, I want to just create some P of n, right, for integers n, that describes this relation right here, which takes in the number of hours worked. N represents the number of hours. represents the number of hours worked, okay? And P of n represents the pay for n hours of work. And that's true for both of these sides, not just for exponential. That's what these two symbols represent. Okay, so let's start doing that by doing just a little investigation here. I'm going to write the table back here, right? We're just going to take a closer look at these numbers. Where do these numbers come from? Okay, so looking now at the exponential pay, right? Let's try to figure out where the numbers come from. We start with, you just walk in, you make $1. Okay, after that, okay, you work 1 hour and you make $2. But where does 2 come from? Well, 2 comes from the fact that 1 times 2 is 2. Because we double it, right? We multiply it by 2. Right? So we double 1, we get 2. Okay. 4 comes from the fact that we take 2, right, our previous pay, and multiply that by 2. Well, what was our previous pay? Our previous pay was 1 times 2. And I'm going to multiply that by 2. Okay, next. 8 comes from the fact that our previous pay was 1 times 2 times 2. Okay, and we're going to multiply that, 1 times 2 times 2, the previous pay, by 2. Notice, every time I'm just tacking on another times 2 here, right? Now it's going to get a little messy, right? Because I have a lot of brackets that I'm going to do. Brackets actually don't really do anything here. But I just want to, the reason I'm using brackets, I want to emphasize that the thing in the bracket is the previous pay, right? So you have essentially, for all of them, it's the previous pay, right? Previous pay times 2, right? Remember, dot is 2. So previous pay times 2. Okay, and that totally works, right? So let's actually write this in exponential form, right? So this is 1 times 2. That didn't change, okay. This is 1 times 2 squared. Okay. This is 1 times 2 cubed. This is 1 times 2 to the 4. Maybe you can guess the next one's going to be 1 times 2 to the 5. For 5 hours of work, you make 1 times 2 to the $5. Right? For 10 hours of work, but before I jump to that, maybe let's look at, for 3 hours of work, you make 1 times 10 to the $3. So let me make a kind of a side table here of writing this in a different way. So this is going to be hours and pay. I'm going to write all of our hours here in a certain color. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the pay we get, oh, I guess I should have started with 0 actually. So let me just cram 0 in here quickly, right? Okay, pay we get is 1, well, just 1. Okay, next one is 1 times 2 to the power of 1, right? 2 to the power of 1 is 2, right? So next is 1 times 2 to the power of 2, right? Because it's the previous amount doubled. Right? So it's 1 times 2 times 2, which is 1 times 2 squared. Right? So that comes from here. 1 times 2 squared. Next one is 1 times 2 to the power 3, and that's for 3 hours of work. And so hopefully you can kind of see where this is coming from, right? So I'm going to bring up another table here quickly. Okay, so our new table looks a little bit like this, right? So the number of hours we work is still our independent variable, and our total pay is still here, right? So you can see that, for just walking in, we get $1, but then for all the other hours of work, we get some power of 2, right? The initial pay times some power of 2. And that power of 2 is the number of hours we worked. 5 and 5 in the exponent there. And that comes from the fact that when we work 5 hours, right? When we work 5 hours, let me zoom in right here. So 5 corresponds to 1 times 2 to the 5, right? In our table here for hours and pay, right? This comes from the fact that we are taking the initial amount, right? And we are doubling it 5 times, right? So hopefully that makes some sense, right? We're taking the initial amount and we're doubling it. Doubling is the 2. Doubling is the 2. 5 times is the 5, right? So if you work n hours, you're going to take the initial amount and double it n times. And so our equation is the pay as a function of n is 1 times 2 to the n, which is just 2 to the n, right? Multiplying by 1 doesn't do anything, so it's just 2 to the n. And that is our exponential function. This is the first exponential function you're seeing, assuming you haven't taken any other courses on this, right? But this is the first exponential function you've seen, and it's this p of n. So this kind of lends us really nicely to just jump right into the actual, essentially the general form of an exponential function. An exponential function, I'll call it f of n for now, right? Because again, I can calculate now, if I work for 1 hour, it's going to be 2 to the power $1. If I work for 100 hours, it's going to be 2 to the power $100, right? But I don't know how to calculate p of 1.5, which would be 2 to the power 1.5. We don't actually know how to put 2 to the power of 1.5 yet, do we? Right? This is, 2 multiplied by itself 100 times. This is 2 multiplied by itself 1.5 times. So how do you do that? That's something we're going to talk about in section 3.3. There is a way to do it. This is a number, right? But I haven't discussed how to actually do that yet. So again, I'm just going to think about this in terms of f of n, just integers right now. F of n will always be, for an exponential function, the initial amount times the, I'll call it multiplier to the power n. The multiplier is like what's happening each time. Doubling, tripling, quadrupling, quintupling. It doesn't even have to be whole numbers. You can multiply by 1.5 each time, right? Multiply by, you get 1.5 times your previous pay. That'd be 1.5 as your multiplier. And this is what every single exponential function will be in the form of. Okay, maybe later on we'll replace n with x so it can take in any number, but for now we are looking just at this. And this is usually written as f of n equals a b to the n. Okay, a is our initial amount, b is our multiplier. And I hope you can see why exponential functions will always be in this form, right? Because exponential growth just works that way. You're always taking your initial amount and multiplying it by the multiplier some amount of times. So you're taking the initial amount and multiplying it by the multiplier n times. So that's what that power is doing for us there. Okay. And also, just something to note here right now, n is an integer. For right now, n is an integer, which means the input to the function is only integers, right? And also something to mention is that the multiplier has to be greater than 1 right now. We're going to deal in the next section with what it means for the multiplier to be between 0 and 1. And then we'll never deal with what it means for the multiplier to be a negative number. Maybe I'll mention that next time because it actually doesn't work. You can't do that. So the multiplier will always have to be between 0 and infinity. But for right now, it has to be bigger than 1. Between 0 and 1, something slightly more complicated happens. Okay, now let's talk quickly about a kind of a break in the pattern, right? Kind of a break in the pattern here, right? You might expect, if you're going down, right, it's 1 times 2 to the 4. Going down is 1 times 2 to the 3. Going down is 1 times 2 to the 2, right? And then going down is 1 times 2 to the 1. Maybe you might guess that this should be 1 times 2 to the 0. Right? But then what is 2 to the 0? This is actually where our definition for what it means to have a power of 0 comes from. Essentially, a power of 0 means do nothing, right? Multiply it 0 times. Don't multiply it. Right? So this is why anything to the power of 0 is 1, right? This is 1 times 1, which is obviously 1, right? So essentially, that is why any number to the power of 0 is 1, because of this moment right here, of this property of exponential functions. We want the pattern to continue. So we just define 2 to the power of 0 to be 1, okay? Anything to the power of 0 is 1, okay? And we make that definition, and it works. And it's actually the only thing that would make sense for 2 to the power of 0. I mean, don't multiply is the same thing as multiply by 1, right? That's the same thing, not multiplying and multiplying by 1. Those do the same thing, right? So that's why anything to the power of 0 is 1. So that's something to quickly mention right here, you know. A to the power of 0 equals 1, with the one exception that a cannot be 0. Okay, so 0 to the power of 0 is actually not a number. So not a number. Well, that's a little bit of an incorrect way of saying it, but it is a indeterminate. Indeterminate. It might not be an indeterminate form, but it is an indeterminate number. So I'll just call it that. In case anyone who knows math is listening for whatever reason, like knows calculus, this is not an indeterminate form, but it is an indeterminate number. Anyways, whatever. Very small side tangent. That is the main point here. This right here. So I'm going to box it. That's the main point of what I'm getting at here. Right? So the whole pattern actually works all the way to 0, right? Including 0 and 1. Right? The pattern actually holds. Right? That we're putting the multiplier to the power of how many times we've used the multiplier. Right? So this is actually, I could put in this box right here, right? 1 times 2 to the 0. Because 2 to the 0 is 1. Right? So we don't change the initial value. Don't change the initial value. Okay, I think we're ready to move on to just talking about qualities of exponential growth. What are some interesting properties we see here in this exponential growth like this? And then from there, we can talk about just a couple examples of how we can use this in real life. And that'll essentially conclude the lesson. So let's just look at the graph and discuss some of the interesting properties we have here. I'm going to open up a note quickly just so I can follow along, make sure my notes match up with what we're talking about here. So the first thing to notice, right, is that growth. So let me just mention here, I'm going to say properties of exponential growth. Okay. So the first property is the graph increases at an increasing rate. So the amount that the graph is increasing, right? So here we go up by 1 point, 2 points, 4 points, 8 points, 16 points, 32 points, 64 points, 128 points, right? Okay, maybe I was off a little bit there, but that's the idea, right? That the amount that we go up by is increasing, right? The increase is increasing. It's kind of like an acceleration that's happening here, right? It's actually hinting at some ideas. I don't know if I mentioned this already. Because let's see, did you see me mention it? Yes, I did already mention hinting at calculus. Sorry, I had to cut some parts out of the video, so I can't remember if that was included there. So yeah, this is still a calculus idea, right? Calculus ideas. I'm not trying to teach you calculus right now. I'm just trying to tell you that these are calculus ideas, right? So don't be too scared of calculus if it's things you're familiar with. Okay, so that's the first important idea that we have here, right? Okay, the next one, we have to take a look at the actual table of values one more time, right? So again, the difference, maybe actually it makes more sense to look here, right? So the difference is not common, right? So what that means essentially, I don't go up by the same amount each time, right? But the ratio is common. What that means is I get multiplied by the same amount each time, right? That's how we define the whole question, right? Is that, well, you get multiplied by 2 each time. Right? So what this means is that as the independent variable increases by a common or a constant amount, right? So if we go up by the same amount, that's 1, usually 1. We think about every day, how much does it go up by, or every hour, whatever. The dependent variable increases by a common ratio. Okay, ratio is like multiplication, right? Or a common factor, right? Maybe factor might be a better word there, right? So factor is what we're multiplying in, right? So this is going up by 2, multiplying by 2, not just increasing by 2 points, multiplying by 2, multiplying by 2, multiplying by 2. Okay? And so let's say you were given this table like this, and how would you figure out how much, if I didn't tell you it was doubling, how would you figure out it was doubling? Right? Maybe you can look at the first bit here, 1 and then 2 and then 4 and then 8. Okay, you can see it's doubling, right? But maybe there's a more complicated way. We actually have a way to do it, right? What if you're going up by 1.75 each time, right? Multiplying by 1.75 each time, and that would be harder to see. So the third property is that if you take any two successive terms, okay, successive terms of the dependent variable, the ratio of those terms will be constant. Now, let me say this let me actually explain what that means, right? If I pick any pair, any two successive terms, any pair that are right next to each other, 5 to 6 of the independent variable, that means right next to each other, right? And I take their ratio, 6, the higher number over the lower number, that'll be 2 for all of them. That constant will be your multiplier, right? Will be constant. It will be the multiplier, right? So if I were just giving you a table of values, you could find the multiplier by just taking any two successive terms, okay, dividing the bigger one by the smaller one, and whatever you get out, that is what you're multiplying by each time. Okay, and if that's constant, if that's always for every two successive terms, right, then it's exponential, right? And for the purpose of this section, it will be constant for the whole thing. Okay, that is essentially all the ideas I'm quite certain that I wanted to go through here. There's one more, it's kind of like way of thinking about why does this increase so much, right? And the idea is that the money you have makes you more money. More money. That sentence kind of encapsulates what exponential growth is built upon. And that's the idea that, well, if I have $1, doubling that is not much of an increase. But if I have $100, doubling that is a big increase. And since I doubled that and got a lot more, if I double it again, I'm going to get even more of an increase, right? So it doesn't have to be just money. The amount of thing you already have, right, also gets doubled, right? And this is why it might be deceiving to say, well, right at the start you might have said, well, $1, that's not really good. And you double that, you get $2. Well, that's not good either, right? So maybe the linear pay would be better. But the thing is that the money you have is making you more money, right? Once you're at that 5-hour mark and you're making, I don't know, I'm looking at the graph here. Oh, it's $32, right? Doubling that is going to get you, twice as much, obviously, right? It's going to give you a $32 increase. So essentially, the amount of money you have is your increase here, in this case of doubling. And that's the idea of how exponential growth works. The amount of thing you already have also gets doubled and makes you more of that thing, which will then again get doubled, right? In the next iteration, the next time you go around doing this, right? So these are all the ideas of what I'm going, what I'm trying to get at here with talking about the nature of exponential growth. This section is called the nature of exponential growth. We're trying to understand, why does an exponential graph look like that? Why does it all of a sudden shoot up? Well, it's because the money you have is making you more money. And that more money is making you even more money. And again, all this works not just with money. It works with anything. In fact, we're just going to go through two examples here of things that, don't double and aren't money. Okay, well, one of them is money, actually. But but the other one's not money. So let's take a look at our examples here. The first one is I want to model, okay, the following thing. Model means find an equation that describes this. A rat colony that triples every year, sorry, and starts with 2 members How do we model this? Okay. Well, first of all, let's define some variables. I'll say P of n is population. I'll say is population in year n of rats in year n. And n is number of years passed. Right? Number of years passed. Okay. And again, just try to remember the formula. The formula that I mentioned to you right up here, which is that essentially this sometimes OneNote jumps around on me. I don't know why. Okay, I'll just rewrite it because OneNote's being annoying. So f of n will always be, okay, f of n will always be the initial amount times the multiplier. And you can think of it as that multiplier is being applied n times. That power of n is like how many times we're multiplying by n. So how many times are we applying the multiplier to the initial amount? Okay, so let's work this out together here. Okay, so P of n is our population. Okay, initial amount 2. Our multiplier 3. We're tripling to the power of n. And there we go. We have an exponential function that describes this. So if I wanted to know in year 3, what's the population? Well, it'd be 2 times 3 to the power of 3. Right? Which is going to be 54. If I did that right in my head. I think so, yep. Which is 54. So you see, it's pretty easy to make an exponential function if you're given it in this form, right? Initial amount times the multiplier to the power of n. And this was tripling, so tripling goes in here. Now let's talk about something that's happening, something that's not being multiplied by a whole number. And this is fine still. The last example we have is a stock price that goes up by a factor of 3/2 every second. So once again, P of n is the stock price at second n, and n is the number of seconds. N is the number of seconds. So again, we always think about our exponential functions in this form. It's the initial amount times the multiplier to the power of n. So this is the general form of an exponential function. This is just generally how it works. Okay, so P of n is the thing where is the actual function. I should have mentioned. Sorry, I have to say I didn't say an initial amount, right? So the initial amount is 25 cents. Right, 25 cents. Okay, so let's take a look here. Well, 25 cents, that's $0.25, right? So if we're doing our thing in dollars, we should keep it, stock price, I should say in dollars at second n. Okay, so 25 cents is $0.25. We're multiplying by 3/2, okay, to the power of n. 3/2 is 1.5, so it's up to you if you want to write it as a fraction or not. I would write everything as a fraction. So in fact, I'd even write that as a fraction. So we have a quarter times 3/2 to the power of n. Notice a quarter is not in the bracket there. A quarter is not being put to the power of n. Okay, so that concludes, I should actually graph these functions. How about I graph them, right? So if I have, I'm going to open up a new Desmos tab here, right? So I'm going to say f of x is, what was our first one? 2 times 3 to the n, which was for our rats. So 2 times, and I want to hide it because again, we don't actually want to know what f of x is. 3 to the, I have to call it x for Desmos, but it's not really what that is. I'm going to say this is 1, whatever, 5. So here is the graph of our rat population. Okay, so the graph of our rat population goes from -1 to, I will say, 15. So there we have it. It's a little small. There we go. So our rat population starts out with 2 members. That's it. 2 members, right? And I guess actually I should start at 0, right? There we go. So it starts out at 2 members, right? That's why we have a point there at 0, 2. And it keeps tripling every day. So you see really quickly, this goes way up there, right? You see how that goes way up there? You know, in how many days? In 11 days, we have 354,294 rats, right? So whenever things grow exponentially, you better watch out, because really fast, you're going to get a huge amount of it. Like bacteria grows exponentially. Rats, like the actual rats and insects and anything living in the wild, rabbits, grow exponentially. In fact, most, well, I can't say most animals, that's not true, but a lot of animals grow exponentially when they're in being studied in captivity, right? Of course, maybe not perfectly exponentially, right? Maybe there's some little bumps. You know, here we have perfect multiplying by 3 each time, but approximately, right? And so in math, we look at the perfect case, so that in real life, we can look at the less than perfect case, but we have some tools to work with. And so the tools we're trying to learn is exponential functions. Okay, enough of that. Let's take a look at our other example here, which was for the stock, which was 1/4 times 3/2 x. And there we go. We can see it looks like this. So you see, we start at 1/4. So it takes a while. You know, before we were at 11 days and we already had 300 and something thousand. Here, we started at 1/4. And so we have very little that's multiplying. In fact, it's not even tripling. It's multiplying by 1.5, by 1.5, right? So we're going to grow a lot slower. But still, eventually, we're going to get way up there. After only 25 days, or 25 seconds, right? I said that was in seconds. After 25 seconds, we're already at $6,000. So even just small, small amounts multiplying by small multipliers will still eventually get huge given enough time, right? The value will get huge. And that is the nature of exponential growth. And on that note, let's conclude this lesson with a little review on everything we talked about, right? So we started with reviewing the different kinds of functions we know. So I'll just say different kinds of, oh my God, I can't type, of functions we know, okay? Then we talked a little bit about linear growth. And then we went through the whole example of comparing linear growth to exponential growth. Okay. And then we talked about the nature of exponential growth. We talked about the general form of an exponential graph, which I think works well to introduce here. Actually, that's technically a later section of content. So maybe if you're following along with the class, maybe your teacher hasn't mentioned the initial value times multiplier to the power of n thing yet. But I thought it makes sense to introduce here, so I just decided to introduce it. And then we looked through some examples of making equations like that. So you may notice that the practice problems for this section may lack a little bit of these last 2 examples, but it'll be more focused on the theory from up here. Okay, well, that concludes this lesson. This lesson was a hard one for me to record, I'll be honest. I kept running into so many issues while recording. So many, just like how I was explaining things, and I had to redo, whatever. It doesn't really matter at this point, but I have been recording this lesson for an hour and a half now, so you'll know how long the actual lesson is. But it's been an hour and a half for me. Anyways, you can book, if you still have some questions, you can of course book a session with me or another tutor by going to the information page for this course and looking to book a session there. Or you can of course always email me or this program at secondteacherprogram@gmail.com. Okay. Thank you so much for watching this lesson. I hope it was helpful for you. Definitely take a look at the practice problems. Of course, I write them to go along well here. And yeah, that's everything. Thank you so much for watching, and I hope you have a great day. Thank you for watching the video. Remember, if you want me to teach you the entire course, visit my website, tutor.ca, and enroll in the Second Teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in grade 11 functions. Have a nice day.